Okay, we are going to start here. Today is February 9th. We are going to be talking for a moment about particle on a sphere. And then from that we're going to see it's a very close step to go to hydrogen atom. And more generally, hydrogen-like one electron atoms. So this would be hydrogen, helium plus, lithium 2 plus, and so on. So the spherical symmetry is retained in one electron atoms. But we add a Coulomb potential. And this is, of course, the attraction between the electron and the nucleus. So, in all the other problems we've been dealing with, you're on a sphere, you're in a box, you're something, it's either zero or something, or a constant, like the test problem that you just turned in, where you put up a constant energy. Now I'm going to put in the Coulomb potential. So the only difference between hydrogen atom and particle on a sphere is in the potential energy function. So we're going to have H of R theta and phi times psi r theta phi equals E psi of r theta and phi. Now, there are some subscripts we need to put here, and there's also a picture we need to draw to get this hydrogen-like atom picture. So imagine we have our usual Cartesian coordinate system with the unit vectors I, J, and K. And to make things simple, we have a nucleus with charge plus capital Z, E. So Z, E for hydrogen would be plus 1E, for helium plus 2E, and for lithium plus 3E. In other words, what is this is the atomic number, right? Hydrogen has a proton, the charge is plus 1. In System International Units, we multiply it by E, where E is 1.602 times 10 to the minus 19 coulombs. That's the charge on one electron or one proton. So this is the SI expression for nuclear charge. Plus 1, plus 2, plus 3 for hydrogen, helium, and lithium. Okay, so what is the total nuclear charge of uranium, atomic number 92?
92E.
Plus 92E, that's right. For carbon, what would it be?
Plus 6E.
Plus 6E. So you get it? Now, by the way, as you go down to the bottom of the periodic table, you'll get all sorts of relativistic effects with the 1s orbits and things like uranium. We're going to stick up here with things like hydrogen, helium plus, and lithium 2 plus. So we have this nucleus. We'll put it at the origin of the coordinate system at plus ZE. And then imagine we have the electron up here. And the coordinates of the electron, there's a theta coordinate from the I or x axis. There is, oh wait a minute, I got theta in the wrong place. That's a phi coordinate in the xy plane. I goes with x, j goes with y, and then up here there's a theta coordinate off the z axis. And then there's a radial distance r. And so the electron's at the point relative to the origin at the point r vector equals r theta and phi. Or if you want to do it this way, r theta and phi. Okay, so we have electron coordinates. We're going to assume the nucleus is fixed, which is a good approximation. If you relax that, there are some subtle effects that you can see, but we won't, at this point at least, be concerned about those.
Where's the electron, that red dot at the top?
Yeah, so the electron is right here, let's say, and that the nucleus is right here, and this should have a charge E minus, the E bar in front of that, so it's minus E, is the charge on the electron. Okay, now, how many quantum numbers will the wave functions of atomic hydrogen have? It turns out they're going to have a whole bunch. They're going to be N, L, M sub L, S, and M sub S. N, L, M sub L, S, M sub S. So we're going to have 1, 2, 3, 4, 5 quantum numbers associated with these wave functions. And the energy, in principle, can be a function of all 5 quantum numbers, N, L, M sub L, S, and M sub S.
This is for all particle on sphere systems?
So, no, this is for hydrogen atom.
Okay.
Okay, so what we said is particle on a sphere owes a lot, or a hydrogen atom owes a lot to particle on a sphere, particularly the angular parts, which are the same, but there's this strange new radial piece that we have to consider. We're going to have 5 quantum numbers we see. And now let's talk about the Hamiltonian for hydrogen atom. For particle on a sphere, it was angles only. You were locked onto the sphere. But for hydrogen atom, we're going to have both radial and angular terms. We're going to have a kinetic energy operator that's a function of r, theta, and phi. And at least at the outset, there'll be a potential operator that's also a function of r, theta, and phi. For particle on a sphere, this potential was equal to 0. So the kinetic energy operators are the same kinetic energy operator in spherical polar coordinates of r, theta, and phi. Now, I want to see if you can tell me, using the Coulomb potential, what this extra expression is.
Wait. The potential energy.
It's the potential energy between two
The
charged
nucleus and
particles.
electron.
So think about second semester physics. about where we are right now, okay?
Is it the whole Q over 4 pi?
Yeah, exactly, yeah, so it's
Oh, I don't know.
plus ZE times minus E. It's the product of the two charges. And let me do it for the more general case so you can just see that. So it's charge 1 times charge 2 in SI units plus ZE times minus ZE. Now, what's down in the denominator? You said it.
4 pi epsilon 0.
I don't remember this. This is a long time ago.
R. Well, he's in physics right now,
Oh,
so
okay.
he's got just a little bit of advantage over you. Okay, so this is Coulomb potential. This is the attractive potential, notice it's negative, between the negative electron and the nucleus with charge plus ZE. Epsilon 0, do you remember what that is?
Epsilon 0?
Uh-huh. It's the vacuum permittivity of free space, and it's 8.85
Okay.
times 10 to the minus 12. Let's see, Newton to the minus 1, Coulomb squared meter to the minus 2. You can look this up in your P-Chem book or in your physics book, okay? So this is the Coulomb potential. R is the radial distance. So notice we don't care, with this potential we have no concern about the angle, just the radial distance. So this potential really is not a function of theta and phi, only the radial distance. Okay, now, what does the kinetic energy operator look like in spherical polar coordinates? I'll give you a clue, it's listed in your book, okay? So, shall we find it and write the whole thing down? So there's a whole section where they write in all this glorious detail the structure of this operator. Let's find that. And it may be back in chapter 7. Let me just quickly look and find this for us. Okay. Okay. Okay, maybe I went the wrong way here. On page 310, 311, I did go the wrong way. Now, let me write this down, and then we're going to talk about some of the implications, which, interestingly enough, you've used in your chemistry classes since you were a freshman. You just didn't know where they came from. So, this kinetic energy operator is minus h bar squared over 2 times the mass of the electron, del squared of r, theta, and phi. This operator is called the Laplacian operator. Just the derivative part, the h bar squared minus h bar squared of 2me is not. So this is the Laplacian operator. You can have it in any curvilinear coordinate system you want. The two we're going to work with in this course are Cartesian, of course, and either cylindrical or spherical polar in this case. So this del squared r theta phi is minus h bar squared over 2 times the mass of the electron. And now let me write out what it all is. There's a radial piece, d squared dr squared plus 2 over r d dr plus 1 over r squared lambda squared of theta and phi. Now, here's what I want to point out. These are pure radial terms. Pure radial kinetic energy terms. And we're going to look at oscillations in the matter wave that go out radially through these derivatives. This suggests that radial and angular kinetic energy terms are coupled. You're taking derivatives, as we'll soon see, with respect to theta and phi. Those are angular kinetic energy terms, but they're modulated by a radial piece. So the radial piece and the angular piece are intertwined in a certain way. And when I show you how they're intertwined, you'll say, oh, that's obvious. But right now I want to make you sweat a little bit in this barren wasteland we call quantum mechanics. Now, what is this lambda squared theta and phi? This is the angular Laplacian. Okay, now, what does it look like?
Is this all coming from the Laplacian operator?
Yeah, so in other words, the Laplacian operator is this del squared.
Yeah.
This is the radial piece, but the angular piece is so involved, it's given its own expression.
Inside the operator.
Inside the operator.
Okay.
And now we're gonna write what it is, okay?
Dang, that's gnarly.
1 over the sine squared of theta, second derivative with respect to phi, plus 1, you see why they didn't write it all out, 1 over the sine of theta, d d theta, sine of theta, d d theta. Holy smoking catfish. Okay, so notice we have 2 types of radial, or angular kinetic energy. We have a phi derivative, so we have angles in the phi directions, curvature, and then we have theta curvature, second derivatives. And this mixed form you might have questions about. It turns out, given the type of the wave function, this is a better way to write it than just writing second derivatives and carrying those terms through. So this is the phi term, and this is the theta term. But notice they're mixed. So we have to somehow solve all this. So how would we solve it? And the answer is, this is a partial differential equation, and we use the technique of multivariable partial differential equations to solve this.
You would start right here though, right?
Yeah, I mean, you start with all of this trash.
But if
This look like, but I'm not going to do that. we're going to have the luxury, you know, if you drive a car, you feel every bump the whole way, but if you get in an airplane, you get there a lot quicker and you don't feel all the bumps, potholes, nor do you stop for red lights
I'm
or any of that
assuming you
stuff.
got an equation for us that this all equals to, that we don't have to solve it ever again.
Yeah, okay, let's see what we're going to do here. Now, what we're going to do is we're going to say the solutions psi n L m sub L s m sub s, the solutions, and this is a function of r, theta, and phi, will be given as the direct, there'll be a normalization constant, and there'll be a radial part, r, n, L of r, those are the quantum numbers, and an angular part, y, L, m sub L, theta, phi. So the problem factors into a product of an angular wave function and a radial wave function. Usually, these are separately normalized. So if you normalize it radially and you normalize it angularly, the normalization constant here just goes to 1. So that's usually the way we do it.
So you normalize them both and then you just...
So you
multiply
do
by
radial normalization integrating over r, and an angular, and basically it says somewhere between r equals 0 and infinity, I'll find the particle. And the angular normalization says somewhere between theta equals 0 and pi, and phi equals 0 and 2 pi, we'll find the particle. So we do that separately. We get an angular and a radial wave function.
I get a little confused when we normalize, because I know you have like this list of equations that all, when you find the derivative of them, they all equal to 1, and I just get confused on which ones to pick. Like when I'm looking at these, I'm not sure what I would even do to normalize those, like what function I should use.
Okay, normalization of a wave function, let's just make a little note.
I'm assuming you normalize it for simplistic reasons. Like you don't have to, but you do it just to make the...
Oh yeah, it's so, with rare exception, it's better to normalize than not to normalize.
Yeah.
Radial normalization means that.
Yeah.
Okay, and we've just assumed that. And then angular normalization, we do the same thing for these things. These things have a special name, they're called the spherical harmonics. And for particle on a sphere, the y, L, m sub L, theta, phi's are the wave functions. In other words, this piece, if we were just dealing with particle on a sphere, their wave functions would be y, L, m sub L, theta, and phi. You'd be done. Because there's no radial part to particle on a sphere, the radius is fixed. Here, I have to have a radial wave function. So there's a similarity between particle on a sphere and hydrogen atom or hydrogen-like atoms in that they have the same angular part, but they have different radial parts. Now, that explains the periodic table, by the way, because how do we arrange the periodic table? We arrange it in groups. And we can talk about 1s, 2s, 3s, 4s, 5s, 6s, 7s orbitals. And what we're doing, if you think of group 1 elements, hydrogen, sodium, you're just going right down the periodic table, but the symmetry is the same. They're all spherical orbits. Okay. Now, if you want to, you can put an S you can graft in a spin function. So we'll do that later. Right now, I'm not so interested in that. And remember, spin is a relativistic effect. So basically, if you put a spin function in later, you're adding relativity to your quantum mechanics. Okay. Now, what do we have here? We have a radial wave function that's normalized, an angular wave function that's normalized. If we want spin wave functions, I don't like what I did there. Yuck. We should just do S, eta, let's see, S, S, M sub S. That's the best way to do it. And we won't go into any more detail than that. So I'm just putting the spin thing on the end, and we're not going to worry too much about it right now. A little bit later on, we'll talk a lot more about it. Now, the only thing we have to do next is find the quantum energy levels. We have the wave functions, radial terms, and spherical harmonics. And we'll get to spherical harmonics in a minute. You know and love them well, you just never recognized them for what they were. The spherical harmonic or angular piece, the same particle on a sphere versus hydrogen atom. The energy eigenvalues E, N, L, M sub L, S, M sub S break down just to E, N. In other words, no effect on energy. So the energy eigenvalues are the Rydberg constant divided by the principal quantum number squared. Now, if we really wanted to get this, we'd have to solve the differential equations. We're just telling you what the result is. Now, let's stop for a minute and look at page 311 on the spherical harmonics. And then we'll go chase down what the Rydberg constant is. How do you account for if it's helium plus rather than hydrogen? What if the nucleus has a charge greater than +1? So we're going to go into all that. I want you to look at page 311. And in specific detail, I want you to look at table A2. Okay, in table 8.2, we have a listing of a whole bunch of spherical harmonic functions. And at the bottom of the table, there's some interesting orthonormality conditions. But now, turn in your book one page ahead. And I want you to look at these drawings. They're on page 313. Let me just hold this up for the camera. Now, what does this sphere look like?
Looks like an S orbital.
An S orbital. What does that next one look like?
Looks like a D orbital.
What does the next one look like?
It's like a D orbital.
You got a D.
What does the next one look like?
F orbital.
Okay, now, look at this. This guy is a fat guy with 2 jelly rolls on the belly. The F orbital.
Yeah.
The D orbital was not so fat a guy with only 1 jelly roll around the belly. So what would a G orbital look like?
3 fat.
3 fat rolls around the belly. Okay? Now, what you know as S, P, D, and F orbitals are nothing more than plots of the spherical harmonics.
Yeah.
So that, in other words, bozos and idiots say SPDF, sophisticated, mature, with it, P-Chem students say, oh, that's the L equals 1 spherical harmonic, i.e. a p orbital. Or the L equal 2 spherical harmonic, a d orbital. Or the L equals 3 spherical harmonic, an f orbital. And you're even smart enough to know that the L equals 4 is a g orbital, which none of those silly, stupid, immature little freshmen taking Gen Chem have the faintest clue about. Don't you feel mature, sophisticated, and with it?
I just feel so good.
I mean, you're all ready to hop into the party bus to Tahoe, right? Wouldn't that be a kick in the pants if I could snag a party bus and drive it all the way to Tahoe?
Yeah.
That would be incredible. Okay, now the other spherical harmonics. The spherical harmonics are not exactly like p orbitals that you know, because px, py, and pz are used for bonding. These are p1, p0, p minus 1, and they look like donuts and toroids and stuff. And you can take linear combinations of these and get the other ones. It's really easy to do. But there they are. So for all practical purposes, the spherical harmonics give you the s, p, d, and f orbitals. And symmetry-wise, it's the same particle on a sphere that it is here. Now, the question is, hey, these guys are having P-Chem. Don't you feel sorry for him?
No,
See the blood running down here?
there's one from you. Actually, I didn't like that class, so yeah, I can see blood running down right
Help.
now. Hi, Ty.
They're being tortured with wave functions.
I can just give you the.
I'm taking the side, the pitchfork side, and sticking him in the rear with it. But boy, the camera's on. I'm in trouble. Okay. So these are like S, P, D, F orbitals. And then we have a radial function. So it turns out that a 3s orbital has more oscillations in it than a 2s orbital does. And so we have radial oscillations of the wave function and angular oscillations of the wave functions. And so the radial function gives us the n quantum number, the principal quantum number, which relates to the number of oscillations radially that go out. So this is a very pleasing picture that we're starting to put together of hydrogen atom. And we want to look now ahead to atomic structure and spectra. And let's look at equation 9.1. Okay. And in equation 9.1, we see the expression of the Rydberg constant and the whole quantum mechanical problem. Now, let me just look at a couple of things here. Oh, if you want to look at the radial function, look at figure 9.1. In the new chapter, oh, let's see, I'm wrong. It's figure 9.4 for the radial function, and the functional form is in table 9.1. Now, let me just hold these out to you. Here are a bunch of radial functions. And remember that the general rule, the more oscillations of a wave function, the higher its curvature, the more energy it has. Okay, think of a flat, pristine ocean or lake versus violent waves. The wavy one has more energy. Okay. Now, let's see what we want to do. Okay. This is the Rydberg constant for hydrogen. So the energy levels depend only on the principal quantum number. This is the Rydberg constant, and this is true as is for hydrogen, with Z equals 1. What happens if we're going to helium plus or something? E sub n equals minus Z squared, Rydberg constant, over n squared. And let me just make sure that I've got that. Yeah, that's correct. Now, would you like to know what the Rydberg constant really is? So, the Rydberg constant is this incredible collection of terms that you get from solving Schrödinger's equation. And so, it is the mass of the electron times its charge to the 4th power divided by 32 pi squared epsilon 0 squared h bar squared n squared. Oh, okay, that's not the Rydberg constant, sorry. That's En, the energy of level N. And the Rydberg constant, okay, the Rydberg constant is all of this. Now, have you had it with the quantum mechanics and you want to see this at a more intuitive level? Of course you do. This must seem like total gibberish. by the way, this problem is rigorously solvable without approximations. You can solve the different electron atom. If you get 2 or more electrons, the electrons repel one another, and it makes the problem much more difficult. I mean, it is nasty.
But it's doable.
No, if you get more than 2 electrons, you go to more than 1 electron, the interelectronic repulsions make it a formidable problem to solve.
Yeah.
In other words, and there's a little problem because molecules have more than 1 electron, inevitably. Look at H2, that's the simplest molecule, right? H2 has 2 electrons. And if you're trying to bond up DNAs, forget it. I mean, they've got millions of electrons. So these are formidable problems to solve. Now, what do the energy levels look like? So if we plot, this is hydrogen and hydrogen-like atoms. So we're plotting energy up like this. Leave yourself a good amount of space. So you start out let me get another marker here. I'm going to draw some vertical lines here. S, P, D, F, G. Okay. S, P, D, F, G corresponds to L quantum number 1, L equals 2 for D, L equals 3 for F, and L equals 4 for G. Of course, for S, what does L equal? 0. Yes. Okay. Now, I mean, if that's how straight a line I'd walk when they pull me out for a DUI, I would be behind bars. Okay, so we start out here. Here's the 1s. Okay. Then here's the 2s, and there are 3 2p's there, and they're at the same energy. Okay, so 2s and 2p. Then we have the 3s, 3p, and we have the 3d. 3s, 3p, 3d. Then we have the 4s, how many F orbitals do we have? 1, 2, 3, 4, 5, 6, 7. So the number of orbitals, equals 2L plus 1. G sub L is what is called the orbital degeneracy. So let's check it out for D. For L equals 2, 2 times 2 is 4 plus 1 is 5, and I drew 5 orbitals here. Now we want the, so we've done 4s, 4p, 4d, 4f. And now we're going to do 5s, 5p, 5d, 5f, and 5g. So that these are all at the same energy. S, P, D, F, G. And how many do I write here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Excuse me. Now, why are these orbitals getting closer and closer together? I'll give you a clue. E sub n equals minus z squared. Rydberg constant over n squared. Now, as n goes to infinity, what will happen? What's the limit of E sub n as n goes to infinity?
0.
0. That's right. So up here, right here is n equals infinity, and there'll be a million things in there. You can't go above this. This energy is increasing, but the n equals infinity is the 0. So all these are effectively negative energies. Now you might ask, what are these intermediate energy levels here in the pattern? And that's a very important question. These have values of what we've called the magnetic quantum number m sub L. So if you recall, m sub L goes between plus L and minus L in increments of 1. And so for the s orbitals, they're all zeros, because the s is zeros. What about for the d orbits? The m sub L values start at what? Okay, what about f orbits? What about g orbits? What about h orbits? -5. Exactly right. Okay, these are values of m sub L, which is historically known as the magnetic quantum number. It also gives the orientation of the orbit, if you want to talk about it in those terms. Okay, so these are the energy levels associated with different wave functions with different values. So we have specified 3 quantum numbers, n, L, and m sub L here. The n quantum number tells us where we are in the chart. The L quantum number tells us whether we're an S, P, or a D, or an F, or a G orbital. I erased the G right here. The m sub L quantum number tells us the various orientations of the orbits. And we know what the energy formula looks like And we know what the wave function looks like, so we're in pretty good shape here. Now, let's take another look at things. This same picture in a highly compressed form, you can see, by the way, as figure 8.7 in your book. So this is how atomic energy levels look. And now we want to talk about spectroscopy, because we're going to be doing spectroscopy of atomic systems in today's lab. Okay, so all right. So in luminescence, which we'll be doing today, we'll pre-excite with an energy source. For us, that will be a laser or an arc lamp. Or electricity. So what we have is a series of energy levels. So let's say so what if I pre-excited up to n equals 3? So I put enough energy to get up to quantum energy level 3. And then I can go 3 to 2, or I can go 3 to 1. For atoms, do we have such a thing as n equals 0? No. The principal quantum numbers start at 1. So 3 to 2 is a possibility. 3 to 1 is a possibility. We can have some other ones as well. Now, it turns out that let's see, 3 to 2, 3 to 1, and we could have 2 to 1, right?
What is that representing?
Okay, now, if you're going from 2 to 1, you're going to get, you're going to need to look for ultraviolet light in a hydrogen atom. If, however, and let me get another marker to signify that, you go from 3 to 2, let's say, this is called the Balmer series. And this series is visible to the human eye. This is called the Lyman series. And it tends to be in the ultraviolet part of the spectrum. You can't see it with the human eye, although our detectors can, if they're set up for UV work, see it. So what we're going to be looking at today are, let's just write out several possibilities. So I'm not going to ever terminate on 1. I'm going to do 3 to 2, 4 to 2, I'm going to do 5 to 2, and possibly 6 to 2. The longer the line, the more the energy. So I'm going to put energy in, start at levels 3, 4, 5, and 6, have them terminate at level 2, and I'm going to measure the energy gap. And you're going to actually see real atomic spectra and measure them. And I just never get tired of doing this. This is really cool stuff. Now, one of the interesting things is you can look at the sun, or for that matter, a distant star, and you'll see all sorts of atomic absorption and emission lines, and you can characterize with great precision what the star is made of. And you can do subtleties like, is the star in a magnetic field? Is the surface plasma layer of the star rotating, coming towards you, going away, or swirling? We can determine all that by spectroscopic measurements. Right here at Concordia, I've thrown a fiber optic cable out of my spectrographs into the sun, and we detected the beautiful sodium doublet emission from the sun. So we could prove right here from Concordia that the sun has sodium in it. So absolutely incredible. And that's what we're planning to do immediately right now, is we're going to get hydrogen out, and we're going to endeavor to measure its atomic spectrum in the Balmer series, terminating at level 2. The Lyman is just too far in the ultraviolet for the equipment we have. And historically, the Balmer series has been very important. Now, keep in mind what we're doing, though, experimentally. We're going from one quantum state to another quantum state, one wave function to another wave function. And in so doing, there is a certain amount of energy involved. So En minus En prime equals hc over lambda, or hc nu bar. The energy difference between the two levels equals Planck's constant times the speed of light divided by the wavelength of light, or hc nu bar, where nu bar is 1 over the wavelength. So now we head into the lab where we measure our first atomic spectrum. And all I can say is atomic spectra are beautiful. They are spectacular, and they are full of information.